Okay, ma'am. Can we start?
Yes, sir.
Okay. Welcome, participants. Welcome to the next session handled by Professor Lalitha from Department of EEE, KPRI Institute of Engineering Technology. On behalf of the management and the organizing team, we feel privileged to welcome our resource person for this session. To tell about ma'am, she has completed her BE in Electrical and Electronics Engineering from Erode Sengundu Engineering College in the year 2007 and ME in Power Electronics and Drives from KSR College of Technology in the year 2009, and she's pursuing her PhD in the area of power electronics for electric vehicle, and she has a total of 12 plus years of teaching and research experience. She is the overall coordinator of EquiPumps Center of Excellence, which has been opened in Department of Public KPR IIT, and she has presented many papers in various journals and international conferences. We feel extremely delighted to welcome for this session, and ma'am, you can kindly take over the session.
Thank you, sir. So good morning to all. In this session, we will discuss about the control system for hybrid electric vehicle and electric vehicles. So these are the topics to be covered in this session. So the function of control system in hybrid electric vehicle and electric vehicles. Next one is the elementary of control theory. The another one, overview of control system, that is the electronic control unit. Next, the control area network, that is CAN. The next one is control variable. The last topic is control technologies for the electric vehicle. The first one, we will discuss what are the functions of control system in hybrid electric vehicle and electric vehicle. The main function of the control system is to minimize the fuel efficiency, to maximize the fuel efficiency and minimize the exhaust emission in the electric vehicle. The fuel efficiency and emissions are mutually conflicting, and some of the reasons why this happens are when more energy is extracted by the IC engine, the exhaust performance goes down. At lower temperature, the chemical reactions associated with the composition of unburned hydrocarbons may not occur. An increase in compression ratio, which enhances the fuel economy, also raises the temperature in IC engine. So the increased temperature increases both the CO and oxides of nitrogen represented by NOx. So the both fuel efficiency and emissions are mutually conflicting, but we have to maximize the fuel efficiency and minimize the exhaust emission by use of controller in electric vehicle. So some of the minor functions are listed down. It can be carried out by the control system part of the electric vehicle. The first monitoring system is battery state of charging monitoring. Next, battery temperature monitoring and electric motor overheating and IC engine overheating. So these are the minor functions carried out by the control system part. The next one is the hybrid electric vehicle drivetrain. So in the hybrid electric vehicle, we know it consists of the internal combustion engine. It has both petrol, that is IC engine, and electric motor part. The IC engine will be operated with the help of fuel. It may be petrol, diesel, or gasoline. The electric motor will be driven with the help of the battery. So the controller part will be used to control the IC engine, power electronics part, and as well as the electric motor parts. So here the motor will be operated with the help of the battery and the engine will be operated with the help of the fuel. The power can be transmitted to the wheel through the mechanical transmission. It is also called as an power split transmission. The mechanical coupler will couple the powers and transmit to the wheel through the mechanical transmission or power split transmission. In the power split transmission, there is automatic gearbox will be there to transmit the power to the wheel. When the vehicle speed is in low, the electric motor part only will operate with the help of the battery. In the medium speed, the IC engine only operated with the help of the fuel. At the high speed only, the IC engine and as well as the electric motor will be operated. In the condition of the IC engine operated, the motor will be act as a generator and it will be generate the power and stored in the motor. So the battery charging will be obtained at the condition of the IC engine operation. So likewise, only the hybrid electric vehicle will be work. There are two construction of the hybrid electric vehicle. One is the series connector, series hybrid electric vehicle, and another one is the parallel hybrid electric vehicle. So during the braking condition, the electric motor is off. So it will be act as a generator and it will store the energy in the battery. So it is called as a regenerative braking. In the regenerative braking condition, when the brake is applied, the brake kinetic energy is converted into electricity and it will be stored in the battery backup. So in this operation, the traction will be carried out and the battery charging also carried out when the IC engine only operated. So there are three operating modes of operation. The one is the electric motor running condition, electric motor alone running, and the IC engine operating condition. And the next condition is IC engine and the electric motor both are operating condition. So in the IC alone operating condition only the charging will be happen. So this is about the hybrid electric vehicle. So it will show the series hybrid electric vehicle. In the series hybrid electric vehicle, the motor only operated with the help of the battery. Here the engine and generator is used to generate the power and store in the battery. So the vehicle will be run with the help of the motor only. The electric motor will send the power to the electric wheel through the power split transmission. Here there is the generator will be used, the engine and generator will be used to carry out the power generation and it will be stored in the battery. So this is series hybrid electric vehicle. So this one is a parallel hybrid electric vehicle. In most of the case nowadays the parallel hybrid electric vehicles are mostly used. As we discussed earlier, this is the mode of operation of hybrid electric vehicle. The first operating mode is at low speed and another one is high speed and another one is for medium speed and last one is braking condition. The first condition is IC alone starting. In the when the IC engine started, the IC clutch is off to on state and the motor will be in motoring state. So the motor will be operated with the help of the battery. So the battery in discharge condition and the electric current is small. This is the vehicle motion at rest condition. In the next state, all electrical will be in on. So the motor will be in motoring state and the battery is discharging and the starting electrical current is high. So the vehicle motion in moving. The next operating mode is IC engine and electric motor starting, that is in the high speed condition. So the IC clutch is on and electric motor is in motoring state. The battery will be discharged and the electric current is high and the vehicle motion is in moving. So next is IC alone cruising. This is also the moving condition of the vehicle. In this condition, the electric motor clutch is open. So the next operating mode is IC engine cruising and battery charging. In this condition, the motor will be operated as a generator. Here the vehicle motion also moving. In this condition, the medium speed will be maintained. So the motor will generate the electricity power and stored in the battery. So the last one is braking. In the braking condition also the motor will be operated as a generator. It is regenerative braking. The braking kinetic energy is converted into electrical energy and it will be stored in the battery. So in the acceleration condition, the motor will be in the motoring stage and the battery will be discharged and the vehicle in motion only. The braking condition, the motor will be operated in generator and the battery will be in charging condition. The vehicle will be in the moving condition only. So here we will explain this hybrid electric vehicle representation in the video. Kindly see this video for the hybrid electric vehicle operation.
Let's talk about hybrids, also known as hybrid electric vehicles. These vehicles have been on the roads in Canada for about a decade now. They're really popular. Hybrids increase the efficiency of the vehicle and lower CO2 emissions and therefore greenhouse gas emissions too. Let's get under the hood. Hybrids use both fuel and electricity, with both internal combustion and electric motors driving the wheels and batteries that store and distribute energy. The essential idea of a hybrid electric vehicle is that these two types of propulsion systems work in harmony. First, a gasoline or diesel or biofuel internal combustion engine. It has two jobs. to provide motive power and to help charge the batteries of the vehicle. Second, one or more electric motors. These motors are located in different places in the vehicle depending on the manufacturer. Both motors are connected to a transmission and out to the driven wheels. The third component is a battery, or series of batteries which store and send out electricity. Batteries in hybrid vehicles don't ever need to be plugged in because their charging needs are met by the management system of the vehicle, so they are never a draw on the electricity grid or your home electricity bill. Hybrid vehicle batteries generally last for the entire lifespan of the vehicle. Now, the way hybrids manage all of this technology is through a kind of mission control specialist, which is in fact a computer or series of computers. They make decisions about where power is coming from and where it's going. Thousands of times per second, they analyze the state of the charging system and figure out what you're asking the car to do. So, while you're driving along using steering, brakes, and accelerator, listening to music from your mobile device, there's a lot going on. Here's a theoretical example of the kinds of decisions that your car might make as you drive in different conditions. If you're driving along at 20 kilometers an hour, the car might ask the battery if there's enough power on hand for the electric motor to be your motive power. If the answer is yes, the internal combustion engine turns off. You are now running on electric power and depleting the battery resources. If the battery resources get too low, the engine comes back on to power the vehicle and to recharge the battery. If you encounter a hill or need to accelerate quickly and go at a high rate of speed, the system may allow both internal combustion and electric motors to give you the speed and power you need. When you coast, your engine shuts off, saving more fuel. And whenever you brake, power goes back to the batteries. That's called regenerative braking. Energy from the rotation of your wheels while you brake works like a power station, feeding the battery so it can store the charge for future use. And when you come to a full stop, the system turns off your engine, saving even more fuel. All systems and accessories continue to function. Lots of technology, all working in harmony, all very reliable. And by the way, hybrids also use a number of other design features and technologies to run at peak efficiency, including a highly aerodynamic, low-drag shape, weight savings, and a much smaller and lighter internal combustion engine. Hybrids are like having the best of both worlds. On-demand power, significant fuel savings and lowered emissions, and smooth, quiet, emission-free electric motive power as well. So, if you are looking to improve the fuel efficiency of your vehicle, want to lower your CO2 emissions, and if you want to lower the fuel costs of your vehicle, consider a hybrid electric vehicle.
So in the video, the hybrid electric vehicle operation and working clearly explained what will happen at the low speed and medium speed and high speed, when the electric motor will run, and when the IC engine, and when the IC engine and electric motor both are running, when the battery is charging and discharging. So these are the working will be carried out in the electric vehicle, hybrid electric vehicle. So it will shows the 4 operating modes of the hybrid drivetrain. The first one is the startup and normal driving or acceleration mode. It is the electric motor only running condition. The next one is the light load mode. In the light load mode, that is the medium speed, the IC engine will be running condition. In the high speed, that is battery. In the high speed condition, the IC engine and electric motor both are running, both are operating condition. In the braking mode, when the brake is applied, the kinetic energy will be converted into electrical energy and it will be stored in the battery. In the battery charging mode is when the IC engine is alone operated, the motor will act as a generator. It will generate the power and it will be charging the battery. So these are the operation of hybrid electric vehicle. Next, we go for an basic control system for IC engine speed control. So we know the control system is consists of the error detector and controller and the plant. When the input is given, it is a desired value, and we can get the feedback signal. The feedback signal is the output of the actual value. So we can compare the desired value and the actual value. We can get the error signal. The error signal is given to the control part. The controller will give the control signal to the plant, and the desired output is obtained with the help of the feedback. This is the normal control system. So in the Control system of the IC engine speed control. The fuel injector is the control element and the IC engine is the plant. Let us assume the desired speed of IC engine is 2000 rpm and the actual speed is 2200 rpm, means an error signal of minus 200 rpm is generated and this negative error signal is fed to the fuel injector. The fuel injector responds to the negative error by decreasing the flow of fuel to the IC engine. So with less fuel, the speed of the IC engine also drops. So this is the control system of IC engine. Next, the control system for hybrid electric vehicle. It's the modern control system also have the single feedback loop and has the desired velocity as the variable to be controlled. So the driver is one of the control element here. If the hybrid electric vehicle is moving too slowly, the driver steps on the accelerator pedal, and the vehicle is too fast, the driver steps on the braking pedal. So in this control system, there are two cases are discussed. The hybrid ECU is the master controller and it controls the other subcomponents of the vehicle such as IC engine, electric motor and power electronics parts also. So this is the control system of IC engine and hybrid electric vehicle. So next we go for our main control part of ECU, electronic control unit. There are multiple electronic control units are needed for the electric vehicle. The first control unit is hybrid electronic control unit. The next one is IC engine electronic control unit. And next electric motor control unit. Next transmission electronic control unit, power electronics ECU, and the last one is battery ECU or battery management system. Next, we go for an control architecture of hybrid electric vehicle. So we discussed most of the electronic control unit. In the control structure, some of the electronic control units are described in the architecture form. First, the hybrid electronic control unit is responsible for the system-wide energy management. The goal of the control is to minimize the fuel consumption. For each liter of petrol, the hybrid ECU tries to provide the maximum mileage. The hybrid electronic control unit commands the amount of torque and power from the motor and IC engine and the amount and timing of power generation to charge the battery. So this is the function of hybrid ECU. So next one is IC engine ECU. The IC engine ECU is used to control the parameters like fuel injection, fuel flow rate and valves operation and valves present in the engine. So the next ECU is electric motor ECU. The electric motor ECU is responsible for switching of the electric motor from motoring mode to generator mode. When the battery is in discharge condition, the motor will be operated. And when the electric motor in generating mode condition, the battery will be charging. So this EM ECU only will give the switching of the electric motor from motoring mode to generating mode and also control the motor to deliver the torque demanded by the hybrid ECU. The electric motor ECU consists of various control strategies such as constant torque control and field weakening control. The next one is transmission ECU. The transmission, we have the power split transmission to transmit the power from the IC engine or electric motor to the wheel. So the transmission ECU is used to provide the correct gear ratio to control the torque and the angular speed of the electric motor and the IC engine. So this is the function of transmission ECU. The last one is power electronics ECU. The function of the power electronics ECU to receive the commands from hybrid ECU to control the inverter energy flow in both ways, that is charging and discharging, to control switching of electric motor between motoring and generating mode, and to control the switching of electric motor. So these are the function of power electronics ECU. Next one is the battery ECU. It is also called as a battery management system. The battery ECU monitors the temperature of the IC engine. So temperature of the IC engine and electric motor also. The battery management system is essential for long battery life and optimum fuel efficiency. So these are about the control architecture of hybrid electric vehicle. Next one is the control area network. The control area network is simply called as a CAN. The CAN is a fast, high rate network enabling communication between ECUs. In CAN, most data can be updated every 10 milliseconds and the data is checked to assure the data reliability. Here we can see in the CAN network, simple CAN network of the hybrid electric vehicle. So the hybrid ECU will control the all other ECUs, all other electronic control unit. The hybrid ECU get the input from the driver in the way of acceleration pedal and braking system and vehicle status and steering command and AC setting. So the hybrid ECU will control the engine ECU. The engine ECU input is speed and torque, speed of the vehicle and torque. It will control the actual torque of the engine. Next one is the clutch ECU. The clutch ECU will get the command as on and off. Next, the output of the clutch ECU is the clutch will be engaged or disengaged. The transmission ECU input is gear ratio, and it will be give the output as a control gear ratio. The battery ECU input is the ampere. So the battery ECU will control the state of charging of the battery, voltage, current, and temperature. So the motoring or generating mode ECU will get the input as a motor or generating mode, and it will be control the torque and charging current of the battery. So next is the traction ECU. The traction ECU also control the torque. The power electronics ECU input is the power flow, and it will be give as a output voltage in current or motoring or generating mode. It will control the switching of the motoring and generating mode. Next on the AC ECU, the AC ECU will maintain the cabin temperature. So the CAN network will the hybrid ECU is the master of the other ECUs. It will control the other ECUs. It will get the input from the driver. The driver input is one of the control elements in the electric vehicle. The next one is the control variables. What are the control variables? What are the control parameters are available in electric vehicle is categorized into three. The one is mechanical control variable, another one is electrical control variable, another one is discrete control variable. The mechanical control variables are the variables related to IC engine, gear ratio, and RPM of each rotational component. The electrical control variables are current in the battery, inverter, and electric motor, the voltage across electric motor, inverters, and battery terminals, and electric motor torque. The other few variables need to be considered for the electric vehicle operation. The one is either the electric motor will be in motor mode or generator mode, and we need to consider the gear ratio, and we need to consider the clutch, whether the clutch is engaged or disengaged. So these are the control variables and the ECU operations. Next, we go for control technologies or control strategies will be used in the electric vehicle. The hybrid ECU is the heart of the control architecture of the hybrid electric vehicle, and it is also known as the energy management strategy. The energy management strategy or hybrid ECU can be classified into the following category. What are the rule-based and optimization-based? The rule-based can be further classified into fuzzy rule-based and deterministic rule-based. The optimization-based is further classified into, there are so many optimization techniques are available for the electric vehicle controller. Some of the optimizations are global optimization and real-time optimization. The global optimization strategies are linear programming, dynamic programming, and genetic algorithm control. The real-time optimizations are EFC minimization, robust control, and model predictive decoupling control. So there are so many optimization techniques are available. So we are focused in this session. We are focusing the rule-based technique only. So in the rule-based technique, there are two classifications. One is fuzzy. In the fuzzy, the fuzzy strategies are predictive, adaptive, and conventional. In the deterministic rule-based control, there are four categories. One is thermostat control, power follower, modified power follower, and state machine. First, we can get the rule-based strategy from the efficiency map of IC engine. So the rule-based control strategies can cope with the various operating modes of hybrid electric vehicle. The rule-based strategies are developed using the analysis of IC engine efficiency chart and the analysis of electrical component efficiency chart. Here we can see the BSFC, that is brake specific fuel consumption. It is the ratio between the fuel consumption and power produced. When the brake specific fuel consumption is 0.8, we can compare the speed of the vehicle and torque. So another efficiency map of IC engine. So this is an example of developing the rule-based strategy using the IC engine efficiency map. Here we have three regions, A, B, C. In the region A, the electric motor only used because in this region the fuel efficiency of IC engine is poor. It will show in the characteristics. In region B, only IC engine is used since the region of high fuel efficiency. In the region of C, both IC engine and electric motors are used. We discussed earlier, at the low speed condition, the electric motor only operate. At the medium speed condition, the IC engine only operate. The battery will be charged, and in the high speed, the IC engine and electric motor both in operating condition in hybrid electric vehicle. The operating performance of the electric vehicle, its characteristic here. It is the characteristic between the speed and torque. In the A region, the electric motor only operated. In the B region, the IC engine only operated. In the C region, both electric motor and IC engine both are operated. So it will show the efficiency map of IC engine. So next one is the control strategies. Based on the analysis of power flow in the hybrid electric vehicle drivetrain, the IC engine efficiency map and human experiences are utilized to design the deterministic rules. So it is one of the technique of the rule-based technique, that is deterministic rule-based strategy. So these rules are generally implemented using lookup tables to split requested power between the IC engine and electric motor. The most commonly used strategies are power follower, modified power follower, and state machine based control. We can see in this control one by one. The first one is power follower control. So in this strategy, the IC engine is the primary source of power and the electric motor is used to provide the additional power when needed by the vehicle. The care is always taken to maintain the state of charging of batteries within safe limits. The rule base is used in the following category. The first one is below a certain vehicle speed, only the electric motor is used. The second one, if the demanded power is greater than maximum power, the IC engine can produce at its operating speed. The electric motor is used to produce the excess power. And the third operating mode is the electric motor charges the battery by regenerative braking. That is, when the brake is applied, the wheel kinetic energy is converted into electrical energy and it will be stored in the battery. And the fourth operating stage is the IC engine shuts off when the power demand falls below a limit at the operating speed. This is done to prevent the inefficient operation of IC engine. So the power follower control is a very simple and effective strategy, but the major disadvantage is that the efficiency of the entire drivetrain is not optimized. That's why we go for an next control, that is modified power follower control. So in the modified power follower control, to improve the power follower control with cost function. The role of this cost function is to strike a balance between fuel consumption and emission at all operating points of hybrid electric vehicle. The rule-based strategies as follows in the flow chart. The first one is we can define the range of operating points. We can define the range of operating points. The range of operating points is represented by the range of acceptable motor torques for the current torque request. We can show the relationship between IC engine and electric motor by the equation, that is the IC engine torque equal to request torque minus K into electric motor torque. So the K is the motor to IC engine gear ratio. When the greatest possible positive motor torque defines one extreme of the operating point range. This value is the minimum of three values. The first one, the driver torque request. The second one, the maximum rated positive torque of the motor at the current speed. The third one, maximum available positive torque from the electric motor according to the limits imposed by the capability of the batteries. The greatest possible negative electric motor torque defines the other extreme of the operating point range. This value is the maximum of the difference between the driver torque request and the maximum positive torque available from the IC engine, and the maximum rated negative torque of the electric motor at the current speed, and the maximum available negative torque from the electric motor according to the limits imposed by the capability of the battery. So this is the first one, that is defining our operating range. The second step of the flow chart is, for each candidate operating point, we can calculate the constituent factor for optimization. It have so many steps. The first step to calculate the factor is to calculate the fuel range that would be consumed by the IC engine. The actual fuel energy consumed for a given IC engine torque is affected by two things. One is hot steady state IC engine fuel map, another one is temperature correction factor. A cold IC engine uses more fuel than the hot IC engine. A cold IC engine correspondingly produces more emission than the hot IC engine. The output of the IC engine for cold and hot operation is, the cold consumption output is hot use into K1 plus 95 minus IC engine temperature by 75 into K2. So likewise for we can have the hot consumption of output equation. The second step in the calculate the constitution factor is to calculate the effective fuel energy that would be consumed by the electric motor for a time of interval. So we can draw the graph between the fuel energy and the electric motor torque. We can find the operating point of state of charge versus electric motor torque, accounting for gain due to regenerative braking. Then we can combine the curves obtained from the state of charging and electric motor torque and determine the equivalent energy by evaluating the curve of speed versus torque. The third step to calculate the constitution factor is to calculate the total energy that would be consumed by the vehicle, and the fourth step is calculate the emission that would be produced by the IC engine. So these are the steps to find the constitution factor. The next third step in the modified power follower control is normalize the constituent factors for each candidate operating point. The goals of minimizing the energy and minimizing the emission can conflict with each other. The most efficient operating point will likely produce more pollution than less efficient operating point. Moreover, the minimizing the amount of one pollutant can increase the amount of another. Hence, the another goal is to allow the priority of the relative importance of minimizing the fuel use and each of the pollutants. The priority will be given by the step of 4 and 5. The fourth step is the apply user weighting function. That is, the relative importance of each of the normalized matrices is determined by two weighing factors. The first is the user weighting for energy and the emission. This is basically a Boolean switch for the user to toggle to choose to ignore the shutdown emission. The fifth step is target performance weighting, that is K target. The target performance weighting factor is applied to the target weighting factor is ratio between the maximum of time average vehicle performance to the target performance. The step 6 is the final step is compute the overall impact factor. The final operating point is the operating point with the minimum impact factor. The strategy improves the overall performance of the hybrid electric vehicle drivetrain, but it is computationally expensive. So that's why we go for an state machine based controller. The state machine operating modes are, the first one is engine, that is IC engine propelling the vehicle. The second one is boosting, that is both IC engine and electric motor will operate. The third one is charging, that is IC engine only running and charging the battery. The transition between the operating point is decided based on the change in the driver demand and a change in vehicle operating condition and a system or a subsystem fault. Here we can explain the operating modes of state machine. The different states of an hybrid electric vehicle. When it is an off state, the clutch is disengaged and the electric motor in off state. So the vehicle is also in the rest position. When the electric motor drive, the IC engine is off and the clutch is disengaged and the motor will be in motoring condition. The electric motor propels the vehicle. It is a low speed condition or starting condition. The next one is the regeneration at low velocity. The IC engine is off, the clutch is disengaged and the motor in generating mode. So in the regenerative braking, with the IC engine is disconnected. And the next, the regeneration with high velocity condition, the IC engine off, clutch engaged, the motor in generating mode, the regenerative braking with IC engine connected. And next, the IC engine drive is on, the clutch is engaged, the electric motor in off, so the IC engine alone propelling the vehicle. The IC engine alone operate the vehicle. The next one is the boost condition. The motor will be in motoring operation. The IC engine and the electric motor propel the vehicle. That is in the high speed. So in the low speed, the electric motor drive only run the vehicle, and in the medium speed, the IC engine alone run the vehicle. In the high speed, that is boost condition, the electric motor and IC engine both operate the vehicle. So when the battery in charging condition, the electric motor in generator state, so the IC engine propels the vehicle and charge the batteries. When the IC engine is stopped, the motor will be in motoring mode. Then the motor propelling the vehicle and the IC engine is disconnected. And then the IC engine start, the motoring in the motoring condition, and the motor propelling the vehicle and starting the IC engine. So these are the different states of an hybrid electric vehicle. Based on the state, the state machine based controller will be operated. So the next type of the controller mostly used in the electric vehicle is physiologic based controller. In the rule based system, the physiologic based controller is mostly used in the hybrid electric vehicle. The hybrid electric vehicle as a multi-domain, non-linear and time-varying plantel. The fuzzy logic seems to be the most logical approach to the problem. Instead of using deterministic rule, the decision-making property of fuzzy logic can be adopted to realize a real-time and suboptimal power split. The fuzzy logic is an extension of the conventional rule-based method, and it has the advantages of robustness. It is inherently robust because it does not require precise noise-free inputs, and the output is a smooth function despite a wide range of input variation. The next advantage is adaptation. Since fuzzy logic controller process user-defined rules governing the system, it can be modified easily to improve and alter the system performance. The next advantage is flexibility. The fuzzy logic controller is not limited to a few feedback inputs and one or two inputs, and it is not necessary to measure or compute rate of change of parameters. So these are the advantages of fuzzy logic based controller. The next one is how to use the fuzzy logic in design of controller. The energy management and control strategy using fuzzy logic controller. The function of the fuzzy logic controller is to maximize the fuel economy and minimize the emission and distribute the driver request for power between two sources. That means between the IC engine and motor. And the second function is maximize the fuel economy at any point in operation, that is provide the dynamic or instantaneous optimization. The third function of the FLC is maximize some other attributes such as acceleration of vehicle. The next one is block diagram of fuzzy logic controller. So in this, the fussification process will be done. In the fussification process, if IC engine RPM is too low, then inject more fuel. That is the fuzzy value associated with the if X, then Z. The statement would be X less than 2000 RPM. In the rule base has a collection of rules. The several hundred rules may be developed and applied. The inference applies the defined rules to the inputs. The defussification transforms the results of the inference process to the crisp outputs. So this is the fuzzy logic strategy which will help to design the controller of electric vehicle. Next, we will explain the fuzzy strategy. The fuzzy logic controller satisfies the minimize NOx emission and sustain the battery state of charging and achieve the desired torque requested by the driver. So we can consider the two of the input from the fuzzy logic controller. The one is acceleration pedal stroke, that is ACC. The another one is electric motor speed. An induction motor can be used in the drivetrain, and the induction motor is directly coupled to the IC engine. Since the induction motor is directly coupled to the IC engine, it will be in the field weakening region. In most of the IC engine operating, the generating torque decreases as the IC engine speed increases. The rated torque has a ratio defined as K to the rated torque at a rotational speed. The positive K means that the induction motor act as a powering source, and a negative K means the induction motor act as a generator. Once K is determined, the torque command will be K into rated torque at a rotational speed. So the IC engine operating mode will be defined in the three states. The one is the low IC engine speed, another one is medium IC engine speed, another one is high IC engine speed. The first low IC engine speed. When the IC engine rotational speed is low, it generates the pollutant emission with low efficiency. Hence, in this operating condition, the torque assistant controlled by the induction motor should be performed. The assistant torque is commanded to increase in proportion to the acceleration pedal stroke as in the conventional IC engine vehicle. So, the torque command in the low IC speed condition is K into acceleration pedal stroke. The second condition is medium IC engine speed. The medium IC engine speed, when the diesel IC speed is medium, it can supply the sufficient torque to the hybrid drivetrain. Hence, the battery recharging control is performed instead of torque assistant control. When acceleration pedal stroke is below some extent, the torque assistant of the induction motor should be achieved to satisfy the driver acceleration need if the acceleration pedal is pressed beyond the some extent. Since the diesel IC engine torque is subjected to saturation beyond 80% of the pedal acceleration stroke, the motoring action of the induction motor is made to begin from this point. Next one is the high IC engine speed. When the speed is high, the torque assistant control is performed as that of the medium speed range. In battery recharging control, the induction motor output power is kept constant. The IC engine can produce more power than in the medium speed range. The factor K should be made to be negatively greater in order to supply more power to the batteries than that of the medium speed range. As the speed increases, the ratio of the power capability of the IC engine to the induction motor increases. Hence, it is beneficial to recharge the battery at high speed range rather than the medium speed range. So, this is the drivetrain configuration for the fuzzy strategy. So, for this drivetrain, we can apply the fuzzy strategy, that is the torque commanded on K into rated torque at a rotational speed. So, we can consider the three mode operations, that is low IC engine speed, we discussed earlier, medium IC engine speed and high IC engine speed. When the electric vehicle is in low speed, the electric motor only run. When the electric vehicle in the medium speed, the IC engine only run and the battery in the charge condition. In the high, when the electric vehicle in the high speed, the both electric motor and IC engine operated. The next one is the implementation of the fuzzy logic. The development of the fuzzy logic is based on the input-output membership function. We can have the two input variables here to implement the fuzzy logic. The one is the acceleration pedal stroke, that is represented as ACC, and another one is the rotational speed of induction motor in RPM. The ranges of the input variables are set as follows. The ACC is set to 0 when the driver does not press the acceleration pedal at all, and set to 100 when the driver presses the acceleration pedal completely. And the speed can vary from the diesel IC engine to the maximum speed. The output is the normalized ratio of the torque command to rated torque at the speed. The input and the output are normalized between the 0 and 1. The input and the output membership functions are shown here. The first one is the membership function of the IC engine. Next one is the membership function of the acceleration pedal. First one shows the membership function of the IC engine speed. So based on these two, we can create the resultant, that is the final operating point. So this is the membership rule base for fuzzy logic. When the input one is low, that is when the IC engine speed is low, when the acceleration pedal is low, the resultant output is medium. When the IC engine speed is low and the acceleration pedal is medium, the output will be low. When the IC engine speed is low and acceleration pedal is in high, the resultant output is very low. When the IC engine speed is medium and acceleration pedal is low, the resultant torque, the resultant value is high. When both are in medium, the resultant output will be medium. When the IC engine speed is medium and acceleration pedal is high, the output is low. When the IC engine speed is high and the acceleration pedal is low, the resultant torque is very high. When the IC engine speed is high and the acceleration pedal is medium, the resultant will be medium. When the IC engine speed is high and acceleration pedal is in high, the resultant torque, that is K dash, will be in the low. So it will show the membership function. So this is a graphical representation of rule based. We can discuss on the example. The entire rule base is shown in the form of triangular membership function. Each triangle has a height of 1. Let us assume the following input, that is the IC engine speed is 1600 rpm and the acceleration pedal is 0.5, means it can activate the fifth rule, that is both are in medium, means the output also in medium. So the K dash, the resultant value, that is the center of gravity value, we can get it as an 0.5. So these are the control strategies available, that is a rule based control strategy available for the hybrid electric vehicle. So there are so many optimization techniques also available, but in this session we discussed about only the rule based technique. In the rule based technique we discussed about the fuzzy logic rule based technique and deterministic rule based technique. Compared to this, the fuzzy logic rule based technique is better one. So these are the, thank you for your patience. So thank you for listening.
Sir? If there are no questions, I take this opportunity to thank our resource person, Professor Lalitha ma'am, for sharing her experience in the field of control engineering in electric vehicle. Thank you, ma'am.
Thank you, sir. Thank you.
We'll end the session now, ma'am.
Thank you.